Welcome back. My name is Jesse. I am a tutor in Melbourne and I also make videos for the GAMSAT as well. What we're going to do today is we're going to do another section 3 sample questions walkthrough video. It's a tongue twister and a half. I don't know how I get through that every time. I've put together another set of questions. These actually went up yesterday. I was hoping to actually have this video out yesterday and then there was an issue with the recording. So this is actually a re-recording of it again to get it right. So there were some audio issues and stuff like that, and I wanted to make sure that it was all clear. I had some audio issues last week. I realized that my mic was not actually syncing up properly, and I was actually only getting the audio from my laptop, which was really not great. So I'm trying to make sure that these are as high quality as possible, both video and audio. So let me know in the feedback if you're happy with it or if you'd like to see something improve. So you may have already actually gone through these. Otherwise, if you haven't, then I'll link it at the bottom and then you can pause this, go through the questions first and then check back through it. If you like to do it question by question, you could also kind of sit through the video and have a go at it, pause it, and then play the video, see the solution, keep working through it that way. It's up to you. You might also be choosing not to do them and bank them up as a bit more of like a practice test once there's more and more. We're up to number 5 now, so hopefully I can get one of these out every single week and that can build up the practice even more. So first of all, we're going to go through Unit 1, which is actually looking at an ECG. So anyone who's done some physiology may already be familiar with this, but remember, don't come into it with pre-existing knowledge if it's outside of first year bio. I would argue that an ECG reading is not first year bio, it's not assumed knowledge. So I've put in some explanations and everything along with it so that if someone were to be in their first year of university, they could still follow along with it. So if you have any outside knowledge, be careful because chances are the question doesn't actually need it. The other thing I forgot, disclaimer, like obviously these are all written by me, these questions. So I do my best to reflect the ACER material, but at the same time, there may be differences. I don't really know how they write their questions. This is based off of my own experience with GAMSAT, with tutoring and things like that. And I do my best to make them reflect the style of reasoning. And I try to make them as kind of complicated as possible. I try to go on the harder side for most. I'll start ranking them based on their difficulty as well in the resources page. So you can kind of see the difference in the difficulty levels of different questions from easy through to really difficult. But ACER questions are quite convoluted where there's lots of little bits and pieces to the reasoning. So doing my best to try and reflect that rather than have things really straightforward where you just kind of read a point off a graph. That's very rare. It does happen, but it's not going to be the majority of them. So we've got below is a standard electrocardiogram output for a single heart contraction cycle. The cycle includes, bit of a typo there, the cycle includes P waves, which are any initial, another typo, need to fix that, upward deflection indicating the depolarization of the atria, Q waves, which are any downward deflection following a P wave. So it's kind of just explaining everything that's in the graph. So you may want to keep reading, you may want to skip over it. So I'm going to skip over at this point, jump to this one because it's a little bit longer. T waves, which is the upward deflection following the S wave, representing ventricular repolarization. So I can see there's connections to actual physiological elements here. Depolarization of the atria is the P wave, and then the T wave is the ventricular repolarization. So on the notes, what I'd probably be doing is just writing P, and then just write like atria deep like that, T vent deep. Repolarization. That would be enough for me on the notes to know kind of what everything represents. I might even draw up the little graph shape and then just kind of put arrows and just say atria, depolarization, and then ventricular repolarization. Then we've got the QRS wave occurs in quick succession, lasting approximately 100 milliseconds in duration. This complex of waves is called the QRS, indicating ventricular depolarization. So we're slowly getting more and more information out of it. Atrial repolarization occurs during this period as well, but is often masked, so we don't get to see that. That's going to be probably important. Any regions of no deflection are referred to as segments, and any interval covering both waves and segments are called intervals. So there's some kind of definitions coming up here. So I'd probably just make note of where they are rather than trying to necessarily write them down, because if I need to use them, they're just going to be there. It saves me time having to write it. I'll probably forget some of those details. So over here below is a table summarizing the typical durations of each interval and segment. Again, with tables, I've mentioned this before, I really don't read them. I just kind of look at what information it's provided. And in this case, It's already summarized it for me there. So then question 1, atrial fibrillation is an irregular and rapid heart rhythm. So that seems important there. Caused by multiple initial signals in the atria, and then causing more typos. I got to fix, they're all going to be fixed before this goes up. The chambers of the heart to depolarize erratically, causing a fast and irregular heartbeat. AFib is likely to be characterized by. So we have to kind of connect the description of the problem to the physiology of the ECG, right? You are not expected to just memorize and know what the ECG readout of AFib would look like at all. It's based on the information given. So don't go into it with like a preconceived idea of what it is. Base it on the information provided. So first one, a higher amplitude P wave. So we can go over here, we can look at what the P wave was. And P wave was the upward deflection causing, that was depolarization of the atria. So the question actually says that it's irregular and rapid. So it's multiple initial signals, but it doesn't say stronger initial signals, right? So therefore that would just be to do with the frequency or the width of the graph, or how quickly in succession each of these waveforms is coming. So it's not going to actually make the amplitude greater in any way. So that one's going to be out. A shorter QRS complex duration. So the QRS was, it said down here, ventricular depolarization. There was no mention about that in the stem on AFib. And so, again, this is unlikely to be affected. And then absence of an ST segment. So that one's this little kind of gap here between the QRS complex of ventricular depolarization and then repolarization. So it's suggesting that there is an absence of this. And then finally, an inverted P wave. So an inverted P wave would mean that rather than depolarizing the atria, you're like polarizing them, so going the opposite way. There is no inversion suggested. It was all to do with the frequency. So that one's going to be out. So by process of elimination, I kind of look at it and go, I don't really know about the ST segment, but it's the only one that's left. So then I would try to go, okay, well, is there a reason why it would be right? So again, ignoring the fact that if you've done physiology, then you might already know about temporal latency and that kind of thing in nerve fibers, and the fact that there actually is a period of time where they kind of shut off, where they can't fire another action potential within a period of time after finishing one. So theoretically, the ST segment probably can't change. But what we could also do is say, well, if there's multiple signals coming from the atria, you may end up with a piling up of these complexes. And so the next QRS wave may be piling into this one and hiding it like that. That seems probable. And given that there's some way to explain it, even though it may not be theoretically true, based on the information, we're not given any information about temporal latency or anything like that. So we don't rely on that because that would be outside of the scope of the exam. So this would be the most correct answer of the 4. Then we have question 2, the duration of the PR interval can be calculated in milliseconds as. So we've got a bunch of different formulas to calculate the PR interval. What I'll do is get rid of all this so it's a bit clearer. And I'll switch colors actually. So the PR interval is just here in red. So we're trying to find a way to calculate it. Now, of course, it's already there and we already have the duration in the table, but they're creating these formulas with pluses and minuses. So I definitely wouldn't try to form an equation from the graph because there's just too many different variations of adding and subtracting that could be going on, and they're probably going to go for a convoluted one. So what I would do instead is I would test each of the answers. So the PR interval plus the QT interval, which is this red line and this blue line. So we're talking the entire duration like this. And then it says take away the QR complex, QRS. So I'll just kind of line this up. This is this red bit in the middle. It says cut that bit out. And then it says cut out the ST segment. So that kind of lines to here. And you can see I have not isolated the PR interval because I've got this T wave still in there as well. So I'm going to say that one does not work. The next one says PR interval plus QT interval, which is again the full duration. And then it says minus 320. So this is where I have to look to the table and go, okay, well, what durations do I have as 320? So I can immediately see QT interval is actually 320. So if I add PR and QT and then subtract 320, i.e. subtract the QT, I just kind of go back to the PR interval. So really this is the QT interval, just written in numbers just to trick people. And so they cancel out and you're back to the PR. So that looks to be the correct one. You could also prove it by looking at the individual bits. You'd have to cut out the QRS, the ST, and the T wave. The QRS has a duration of 100. the ST segment has a duration of 60, so that's 160. And then the T wave has a duration of 160 as well. And that altogether is the 320 that makes up the QT interval. And so because it's a maths one, I wouldn't really bother checking the others if I was trying to move quickly. If I had enough time, then maybe I'd just check each of them. So we'll do that now. QT interval minus QRS is literally not even related to it. So if I get rid of all of this again, it's saying take the QT, the blue section, and then cut out the QRS. And you're actually left with the ST and T wave. So that would not make sense at all for the PR interval. And then the QT interval minus 80. So again, QT, 80 was the P wave, and that's it. There's no way else to make 80. So that would be taking the P wave off of the QT wave, which doesn't make any sense as well. So that one would be wrong. Then question 3, we have the frequency of the PT interval is estimated as. So this is where now a bit of wave theory, which I cover in the most recent physics crash course video from last week, is being used. So frequency of any wave is the inverse of the time period or the interval of that wave. So we're looking for the PT interval. Now this is a bit of a trick because if you look to the question, there is no PT interval in the table. There's not even a mention of it on the graph. So what this is doing is relying on this definition of what is an interval. And it says an interval is any section covering both waves and segments. So we go, okay, well, if the PR interval was from P to R, and if the QT interval was from Q to T, well then surely the PT interval is from P to T. So P to T from here all the way across to T, that would be the PT interval, is the entire thing, right? Which we worked out before actually we didn't actually do it. So it's all the way from here to here. So the PR interval has a duration of 150 milliseconds. The QT interval has a duration of 320. So putting that together, it means the PT interval has an interval of 470 milliseconds. So what we have to do is then convert that into seconds because milliseconds is not standard units. So that would be 0.47. And suddenly now we can work out the frequency of this interval. So 0.47, I would just say, well, that's around about half. There's no point being exact here, and we get 2 hertz, just like that. And so again, maths question, we can just calculate A. But notice this is an example of a maths question that still uses scientific knowledge and reasoning. So everyone's kind of looking at it as like, I'll just approach it as a maths exam. I still don't think that's the right way to go. I think maths skills are becoming more and more prominent, but you won't be able to actually use the maths until you understand how to interpret it into a maths equation. And that comes from the bio, the chem, and the physics. So the other ones are tricks in there. So 2 millihertz, that would be getting the units wrong. And the other 2 here are just basically about taking the 500 millisecond estimate and getting that jumbled with the formula itself, timesing instead of dividing. So A would be the answer there. And then finally for this stem, we have heart rate is calculated as the number of sinus rhythm cycles that are recorded per minute, and it's expressed in beats per minute. At rest, a person's heart rate is 60 beats per minute with regular intervals between T waves of the preceding sinus rhythm and P waves of the successive sinus rhythm. This interval is approximately what? And it's going to be in terms of a PT interval. So we already got the PT interval. That was 470 milliseconds. And we've got this statement here. It's talking about there's a regular interval between the sinus rhythms. So if I just draw out a couple of sinus rhythms as best I can, like that, there's one with the P and the T waves on the end. Then we've got this interval, and then we've got another, something like that, right? Very, very artistic. So it says that the interval between the T waves of the preceding, so the previous one, there's the T wave, and the P wave of the successive, that interval there is going to be regular, and we're trying to work out what that interval must be. So if the PT interval from here to here is 470 milliseconds, we already worked out that the frequency was 2 hertz, right? So 2 hertz would mean 2 cycles per second. If we're talking in minutes, well then there's 60 seconds to a minute, so that would replicate, or that would be equivalent to 120 beats per minute. But that is not factoring in that there is going to be a gap your heart's not beating instantly right after the next one, right? There's a slight gap, and that's what we're looking at here. So if we factor that in, now our time interval is actually 470 milliseconds plus x, right? Plus some unknown amount. If we do that in seconds instead, it's 0.47 plus x, which is basically half plus x, like that. So we could look at this in two ways. You could either say, well, if the actual heart rate is 60 beats per minute, what that means is that we've effectively doubled the interval, right? T has doubled to halve the rate, right? And so it's a bit of a trick because you might start thinking, oh, then it's C. But that would be the new interval is twice the old interval. We're looking for what's the extra bit, what's X. So really what that means is we've had a 100% increase, we've added on another amount of that same interval. So the answer is going to actually be A. The new, or the interval between the sinus rhythms is equal to the PT interval. We've effectively doubled it, right? There's a more mathematical way to do it though. You could also look at this and go, okay, well, if my new interval is 0.5 plus X, and I know that the frequency, if it was 120 beats per minute down to 60 beats per minute equates to 1 beat per second, which is 1 hertz. And so therefore 1 hertz is equal to 1 on the time interval, like that. And then we can solve this. We can do a switch out here and here, and then 1 divided by 1 is 1. So 0.5 plus x is equal to 1. So therefore x is equal to 0.5. And you can see if x is 0.5 seconds and the PT interval was 0.5 seconds, well then it means that it's equal to the PT interval, like that. Cool. All right, so that's again a bit more of a maths heavy one, but it's also relying on understanding what the sinus rhythm actually is. So you couldn't come at that as a purely maths question, because otherwise then you would get stuck on building up the formulas themselves. All right, so then unit 2, I will clear some of this off because we're probably going to need some of that space. Got a bit out of control there. All right, cool. So unit 2 now, again, I've taken this data from an actual empirical research report. So I've left the link there to reference it. If you do want to go through and read it, feel free, but again, try to do the questions first because sometimes hints at answers might actually be given. I'm kind of cherry picking information effectively to hide some of the obvious statements and then turning those into reasoning questions, right? So a study into the effects of wavelength of light on pigmentation in rose plant leaves was conducted. 2 photopigments, carotenoids and anthocyanin, and an oxidative stress marker, malondialdehyde, I hope I'm saying that right, MDA, were measured in the leaves under different light spectra and photosynthetic photon flux densities. That's a lot, right, to take on. So you are not expected to know about any of that stuff. This is just designed to confuse you, right? So first of all, we've got 2 photopigments. I'm just going to make mention of those. They're our photopigments. And then this other thing, MDA, which we're going to call it, is an oxidative stress marker. Cool. We just go with that. Measured under different light spectra and then also photosynthetic photon flux densities. So I can recognize a few words like flux. I know from physics, the amount of magnetic field that is threading through a wire. So I would imagine that this would be something to do with densities of photons. So effectively light intensity on a particular surface. I'll kind of loosely say that's what it's probably going to be. Then we've got 3 graphs here and it says carotenoids, which are the A graph, anthocyanin B and MDA-C, content in the leaves of rose plants grown under different light spectra, so blue light, red light, white light, and both blue and red, under 250 and 1500 micromole per square meter of ppfd per second. So it is per square meter per second. So that's kind of confirming what I was thinking before. And then it also says that black bars are the 250, so lower intensities. And then 1500, the gray bar, is the higher intensity. So we have quite a few variables going on there. We've got effectively now bar charts with more than just 2 variables. They like to do this in the test. Carotenoids are a photopigment that gives the yellow, orange, and red coloration to a variety of fruits and vegetables. Anthocyanins are a photopigment that gives a blue-purple coloration to certain vegetables. So this one, I just see carrot anyway, so I'm just going to go, cool, that's my orange, and this one here is my blue-purple. Cool, and I'd write that into the notes on the scrap paper. The most light-sensitive compound in rose leaves grown under blue light is or are. Okay, so I can see keywords here are going to be light-sensitive, so responds kind of dramatically to light change. And we're looking specifically at blue light, and we're trying to make decisions between each of the three different compounds. So if we look to the blue light on each of them, then we're going, okay, what's the independent variable? So blue is staying constant, but what is changing? That was the light intensity. So that must be the ppfd, going from black to gray bar. So if I look at this, I go, all right, carotenoids, do they respond to it? From black to gray, they do, decreases slightly, but it's not a big jump. If I look at this one here, that's a more pronounced jump, right? It drops to about 50%. So you get a 50% reduction. And then this one here, same thing, it looks to be about 100% growth, right? Now the trick to this is it may seem like C is the most correct answer because it doubled, whereas the other one halved, right? But it didn't say that light was increasing or decreasing, it just said light sensitive. So what that means is it's bidirectional. So if I look at anthocyanins, there's a 50% reduction when I increase the ppfd. But if I were just to reverse that relationship, if I was to decrease the ppfd, suddenly then it would be jumping up, and that would be 100% gain, right? Which is equivalent to the gain that we get when we increase the ppfd over here. So it's bidirectional. So both anthocyanins and MDA are actually equal in terms of their sensitivity to light. It's just that they have opposite directions that has an increase or a decrease. So the answer actually ends up being D for that reason. Cool. Then we have number 6, consider the following statements. So whenever you get these, just skip over the statements, look to whether they're asking you for false or true statements or something else. And now we know we're looking for false statements, and we just reason with each of them, and then we'll have our answer. So oxidative stress is directly related with wavelength of light. So here it's using a bit of word association. So we knew that oxidative stress was measured by MDA. So more MDA means more oxidative stress. And it says directly related, meaning that the two variables move in the same direction. And the variables are MDA content and wavelength of light. So I go to my MDA graph, which is over here. Again, let's clear some of this off. And I can see that if I try to change the wavelength of light, I'm going to go from red to blue, right? Oh, that's a bit far. Red to blue. So red light is low energy, long wavelength or high wavelength. Blue light is high energy, low wavelength. That would be expected to understand that, right? That would be considered year 12 physics content, and it comes up in chemistry anyway, and bio. So from red to blue, so what I'm doing here is I'm decreasing the wavelength, right? Going from red to blue, and then I look at what happens to the MDA content. The MDA in the certain individual light intensities decreases very slightly. So because that's also decreasing, that is a decrease in oxidative stress. And because it's decreasing wavelength is decreasing oxidative stress, that is a direct relationship, which makes that true, which means that is not the answer that we want. So therefore 1 is actually out because we're looking for false. A cabbage grown under blue light will appear more orange in color than when grown under white light. So obviously this is with rose petals, or rose leaves, but we're going to now extrapolate that to a cabbage plant. And then blue light, first of all, and we're looking for orange color. So orange was determined by carotenoids. So we're looking at blue light, and then it says compared to white light. So we're comparing these two. I can see in blue light, there's less orange. In white light, there's more. So it would actually be that it would appear less orange rather than more orange. And so that one's false. So therefore 2 is actually one of our answers that we want. And then an increase in ppfd reduces oxidative stress in most cases. So again, oxidative stress was MDA. I'll just get rid of all this. And it says in most cases, there's no mention of light. So it means we have to look at that in all cases of light wavelength. So increasing ppfd is going from the black bar to the gray bar in each case. And we can see that as we do that, that increases MDA. Increases. So that would be increasing oxidative stress, not reducing it. So this one is also false. And so therefore 2 and 3 are actually both the answers we're looking for. So therefore the answer is D, just like that. So you don't have to test each of the options you're given. You work through the statements, and then that will lead you to your answer. Obviously then, if your answer that you get, the combo that you get is not there, it means check your work because something's going to be off, right? Next up we have number 7. So some types of wild carrots are deep purple in colour. There are 2 leading theories as to what may be contributing to this. The first is the theory that genetic mutation has caused the coloration. So we're going to highlight that. Genetic mutation. And the second argues the light dependency of carotenoid and anthocyanin pigments in the root vegetable, and that a similar pattern has a similar pattern as observed in the rose plant leaves could be seen in the root of the carrot plant when the leaves of the plant are exposed to varying wavelengths of light. In other words, the second one, I'd try to summarize that because it's very wordy. The second one just says it's because it's doing exactly what the rose leaves are doing in the experiment. And there we go. So one says mutation. This is number 1. The other one says that it's the photopigments responding to light. That's number 2. Which of the following experimental procedures would best determine which of the 2 hypotheses is most true? So these are really tricky, right? And I wrote this one because I know when I sat in March, the one question that still caught me out, and I don't know if I got it right or wrong, but I would hope that I got it right because I felt pretty confident when I finally reasoned it out. But there was a question on like 2 different hypotheses, and you had to choose which of the experimental setups, and it was actually pictures, would best test the accuracy of either hypothesis and allow you to determine which one was true or which one was most accurate or correct. So it's really tricky because you're thinking about how the empirical process would actually confirm something accurately, but also why there'd be a redundancy or no need to test the other hypothesis on the back of the results of the one that you're looking at. So here we're testing whether or not it's genetics or light sensitivity of photopigments. So comparing the colors of a sample of 100 carrots with half grown under natural light and the other half grown under blue light. It already seems very simple. There's no mention of genetic controls. So we don't know whether or not we have genetic mutation underlying there as well. So we wouldn't know if the change in the coloration of the plant is actually due to genetics or due to the light sensitivities. So that one already doesn't look very good. Genetically modifying carrot plants, producing offspring generations from genetically identical parents, and then growing the offspring in natural light and observing the color of each in comparison to the parents. So the first bit sounds pretty good because it's like controlling the genetic variation. So you're removing the effects of mutation. But then it doesn't say anything about changing the color spectra, right? The light spectra. It just says put them in natural light and then just see what you get. So that would really only be testing about the kind of homogeneity of that particular species. So that really wouldn't work for comparing these 2. Breeding a wild type purple plant with a genetic clone and growing equal proportions of the offspring in either blue light or red light and observing the color change. This one starts to sound a little bit better now because we've got a purple plant. We're cloning it, so we're going to assume that there's no mutation there because we're not following the natural process of cell division, but instead trying to regulate and control the mutation and prevent it. And then it also says putting it in either blue light or red light, so we've got variation of color spectra. That sounds pretty good. And then D says breeding a wild type plant with a genetic clone and growing equal proportions of the offspring under blue light, red light, or natural light, and observing the color change. So this one's almost identical, right? The only differences are that it says that it's still a wild type plant. Everything else is the same, but it says natural light as well. The other one just said blue and red. So technically you should always have a control group, and the control group has no independent variable. The independent variable is the wavelength of light being exposed. Given that red and blue are not natural wavelengths that would be controlled in the world, it would be natural light, so a mix of all the wavelengths, then this here has a control for true comparison because then you know what your baseline is. So it's slightly improved on C, and so therefore D is the answer. All right, easy. There we go. So that's 8 more questions that are up there now. You can go through those at your own pace if you want to kind of redo them as well, because I'm trying to just create these so that people don't have to use up all of their ASA material immediately. I'd still say exposure to the ASA material is the most important thing, but I know as well that especially if you're sitting in a second time, you've kind of already used that, then it's quite difficult to really find anything that's going to be similar in the reasoning. I mean, hopefully I can get to a point where I can kind of bank up a lot more and put together like full length practice tests and that kind of thing. But at the moment, it's really just a case of making sure that I can get some out. They take quite a while to write these, like 8 questions here. There's probably a good 2 to 3 hours that goes into at least putting them together, probably more in most cases, because I don't really want to just rush them and just have them be really basic where it's just kind of theory based, because they're easy to write but they're not really reflective of the test. I think at the moment keeping one banging out every single week is pretty good, so hopefully these are all coming in handy. All right, easy. I'll leave that one there and I will see you in the next one.